Hi, welcome to my channel, Jabber Time. Today I'm going to go over powers and radicals. As you could see, I have enough rules right here, and the main thing is the absolute value equation. So let's get started. This slide has a lot of notes. It's all about the power rules, the product rule of powers, the power to a power rule, the quotient rule, the zero power, the negative exponent in the numerator, and the negative exponent in the denominator. Let me break it down one by one. Here's the first one. The product rule of powers. When you multiply a to the power m times a to the power n, you add the exponents and you keep the base. Sometimes students they multiply the base, and it's a common mistake. Here's the rule written by hand. A to the power m times a to the power n equals a to the power m plus n. So you keep the base and you add the exponents. To support that, why it works, 7 to the second times 7 to the third, if you want to apply this rule, you add 2 plus 3 and you keep the 7. So 7 to the power 5. Differently, if you look at the left side, what is actually 7 to the second times 7 to the third? It is 7 times 7 multiplied by 7 times 7 times 7. But that's 5 sevens as a product of factors, which is the same thing as 7 to the power 5 on the right side. So that, yes, you need to add the exponents and keep the same base. Let's try some examples. A to the power 5 times a to the power 2 will be a to the power 5 plus 2, which is a to the power 7. How about a to the second times 8 to the third? We're going to add the exponents 2 and 3, and we're going to end up with 8 to the power 5. We keep the base. I keep repeating that. How about if we have negative exponents? 5 to the 6 times 5 to the negative 2 will be 5 to the 6 added to negative 2, which is 5 to the fourth. 7 to the power negative 3 times 7 to the power negative 9. Add the exponents and you end up with negative 12 as an exponent. Last one, 10 to the power negative 5 times 10 to the power 6 will end up 10 to the power 1. 6 and negative 5 is 1. Let's jump to the second rule. The second rule says power to a power. So a to the power m to the power n, you multiply the exponents m and n and you keep the same base, keep the base. It sounds like keep the change. So 5 to the second to the third, if you want to apply this rule, will be 5 to the second multiplied by 3, which is 5 to the 6. Let's see how it works and why it should work. On the left side, what does it mean when you have a number here in the base multiplied or raised to the power 3? You multiply by itself 3 times. But that's 5 to the second and 5 to the second and 5 to the second, which could be written as 5 times 5, 5 times 5, and 5 times 5. Without parentheses, it's going to look like this. We don't need the parentheses. I had them just to show you that this is coming from this and this is coming from this and so on. So how many 5s do we have? 1, 2, 3, 4, 5, 6. Let's go to the right side. What is 5 to the 6? It's basically 5 multiplied by itself 6 times. So same answer. So this is how the rule works, and this is how you should apply it. Let's try some examples. A to the 4th to the third, you multiply 4 times 3, and the answer is a to the power 12. How about the other way around? A to the power 3 to the power 4. I switched the 3 and 4. It doesn't matter. 3 times 4 is 12. Same answer. How about a to the second to the fifth? Multiply 2 times 5, and the answer is 8 to the 10th. If I'm going a little bit fast, it's just like trying to save some time from a lengthy video. And also, I write the notes before recording to save some time and show you more examples. That's the reason why I'm trying to go fast to show you more and save you some time. I write it earlier. So 10 to the power 6 to the power 6, again, that's 10 to the power 36. One more, 7 to the power 5 to the power 3 will be 7 to the power 5 times 3, which is 15. Let's go to the second rule. Second rule says quotient rule of powers. So if you divide a to the power m over a to the power n with the same base, you keep the base. One more time, keep the base, or keep the change. A to the power m minus n, you subtract the exponents. Of course, we cannot have a equals 0 because that's gonna end up 0 to the power something over 0 to the power something else, which is 0 over 0, which is undefined. So those, formally speaking, we have to mention them. A to the power 5 as an example to show why this works, over a to the power 3 is a to the power 5 minus 3. You subtract the exponents and the answer is 8 to the second. But 8 to the second means 8 times 8, which is 64. Let's see on the left hand side how we could see this in a different way. Well, that means I have a fraction of 8 times 8 times 8 times 8 times 8, 5 8s on top, over 8 to the third, which is 8 times 8 times 8. Cancel 3 8s, and what do you have left? 2 8s. That's 64 again. Now let's apply it for some examples without showing all the details. We don't need the details anymore. 10 to the power 7 over 10 to the power 3. Keep the base, subtract the exponents, and you're done. 10 to the power 4. How about 10 to the power 6 over 10 to the power 8? 6 minus 8 is negative 2. Some books, they say finish this and write without negative exponents. If they say so, you have to flip it, take the reciprocal, and change it to a positive exponent. That's one of the rules in powers, which is coming right after this rule, which is differently 1 over 100, and that's 0.01. Actually, the rule after this one is the power of 0, so the one after will show. Here we go. The power of 0, 0 power. Maybe I didn't say it right, the power of 0. It's the 0 power. So a to the power 0 equals 1, provided that a does not equal to 0, because we don't want to end up with 0 to the power 0. 5 to the second. One more time, this is like how to show you that this works. I'm trying to approach the problem from different angles to show you that yes, it does work this way, and you have to follow the rule and believe in it. 5 to the second or 5 to the second, if you want to use the rule of subtracting exponents that we had a few minutes ago, that's going to end up 5 to the second or 2 minus 2, which is 5 to the power 0, and that is 1. How about on the left hand side, or the left part, if we approach it differently? Well, what's 5 to the second? It's 25, and 5 to the second is 25. Divide 25 by 25, it's 1. Same answer. So let's apply it quick for some examples. 10 to the power 0 is 1. 7 to the power 0 is 1. 711 to the power 0 is 1. That's not the store 7-Eleven, it's just 7-Eleven. This is what I meant negative exponent, that you take the reciprocal or you flip it and make it positive exponent. So here's the rule. A to the power minus m equals a 1 over a to the power m. You change it to positive, provided that a does not equal to 0 and m is positive. Well, if m is positive here with a negative sign, that means the exponent is negative. That's what it means. So this becomes positive. Here's an example. 10 to the power negative 2. If it's a multiple choice, students sometimes make mistakes and picks on negative 100. They think that 10 to the power 2 is 100, so 10 to the power negative 2 will be negative 100, which is not true. 10 to the power negative 2 is according to this rule, 1 over 10 to the power 2, which is 1 over 100, which is 0.01. Let me support that using scientific notation, even though it's not our topic. But it's part of the game. 5 times 10 to the power 2 means 5 times 100. And if you see the 5 as 5.0, you want to move the decimal to the right 2 places, becomes 500. Which makes sense. 5 times 100 is 500. And that's kind of like showing that I moved the decimal to the right 2 places. How about 5 times 10 to the power negative 2? Well, that shouldn't be 5 times negative 100. It should be 5.0 to show the decimal times 10 to the power negative 2. You move the decimal to the left and you make it smaller, becomes 0.05. To support that one more time, I could write this as 5 times 10 to the power negative 2 as 5 times 1 over 10 to the second, applying this rule right here, which means 5 times 1 over 100. Multiplying fractions, you end up with 5 over 100, which is 5 hundredths, 0.05. So, just keep in mind, 10 to the power 2 is a big number, 10 to the power negative 2 is a small number, which is 0.01. That should help or support that, yes, I should divide or flip it to make it small. Let's take a negative exponent in the denominator. Pretty much it's the same rule, but it shows in the denominator. Then you flip it and becomes a to the power m over 1, where we don't need to write 1. I'm not reading the rest right here. We kind of like know it, and it's pretty much similar. So what's 1 over 10 to the power negative 2? If they say leave your answer without negative exponents, you have to flip it, as the rule says, and make it 10 to the power 2. How about 1 over 5 to the power negative 3? Becomes 5 to the third. Next, let's try some different examples as a warm-up for the coming problems and radicals. If it says extract roots to rewrite each radical expression, I have in this page 1 problem, and the coming page 3 more problems. But I just want to take my time for the first one. To extract the roots, we need to look into 48, and if you take your time and do the prime factorization, that's what I have. 2 times 24, 2 times 12, 2 times 6, and 2 times 3. So 48 is 2 times 2 times 2 times 2 times 3. If you put this inside the square root instead of 48, I have the following. But notice the 2's. I could see it as 2 times 2 and 2 times 2. 3, leave it alone. I cannot simplify square root of a 3. 3 is not a good number to deal with square roots. It gives you a rational number or decimal that is not repeating, not terminating. So, differently speaking, that's square root of 4 times 3. You could break it down. Square root of 4 is 2, square root of 4 is 2, square root of 3, you keep it as is. And the final answer is 4 rad 3. That's how you do it in lengthy detail. How about if you want to do it quicker than this? Here we go. Square root of 27, square root of 32, square root of 300. Looking at perfect squares, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and then we have 25, 36, 49, and so on. Those numbers are perfect squares. And if you take the square root of 25 is 5, square root of 49 is 7. So they work nicely with the square root. So looking at 27, inside 27, I know it's multiples of 3's, but I could see the 9. So I could rewrite 27 as 9 times 3 and break it down. Square root of 9 is 3. Square root of 3, you keep it as is, and that's it. Now 32 doesn't have 9s. How about 16? 16 times 2. One more time, same style. Break it down, finish it, and you're done. 300, you're gonna go like 2 times 150 and so on and so on. That's not gonna help much. How about all the way? 100 times 3, because 100 is a perfect square. So you break it down, and that gives you 10 square root of 3. Let's move on to something different, which is an activity that says the following. Match each expression to an equivalent expression in the box at the right side. For each given expression, make sure that a does not equal to 0. We don't want to deal with zeros, as you know. Like this is going to end up 0, this is going to end up 0 over 0. We don't need that. I'm going to save you some time and do the work. You could refer to this. I'll put this in the description as timestamps. So anything you want to visit, you could just jump to it using the timestamps. First one, a to the power 3 times a to the power 1. That is a to the power 4, which is right there. A to the third over a to the 7. That's 3 minus 7, which is negative 4. And that is right there. A to the 4 times a to the negative 4, add the exponents, you end up with 0, right? And that's 1. You go up here. Next one, you're going to distribute the power 2 outside to each factor inside. This becomes a to the power 1 to the power 2 and a to the second, b to the second to the power 2. 2 times 2 is 4, and that's the final answer, which is down right here. A to the second, a power of a power. You multiply the exponents, and you end up with a to the 4. Subtract exponents here, you get a to the power 0, which is 1. Here, distribute the half as a power to a to the 8 and b to the 4. Half times 8 is 4. Half times 4, because we multiply the exponents, is 2. And that's the final answer, which is down here. Last one, a to the second times a to the minus 6. We have the same base. We keep the base. We add the exponents. And the answer is a to the power negative 4, which is up here. Okay, now let's move on to something else, which is radicals and powers and absolute value. One more time, everything's going to be in the time stamps down below. So this one's going to be called match each expression. In this right here, they gave me a table that is 2 in 1. And they gave me the graph, which is y equals cubic root, square root of x to the second. I know it's kind of tiny, but I do have it right here, and it's right there. For each value of n, we have another one coming when n equals 3. In this case, n equals 2. The nth root of x to the power n, in our case, it's going to be the second root of x to the second. Analyze the table and the graph. Identify the function of family associated with the graph and write the corresponding equation. Let's take a look. First, to do anything with that, you have to compute what's inside, then apply the square root. So it's like a 2 steps or composition of functions, one after the other. That's my input x. You square it first, you get x to the second, you apply the square root next, and you end up with this as an expression. How about if we start with 2? This 2 right there. Well, 2 square it, you get 4. 2, you get 4. Take the square root now, takes you back to 2. Takes you back to 2. So you start at 2, you end up at 2. Let's go with negative 2. This is to support that, so we'll just keep it. Let's go with negative 2. Negative 2, square it, it's 4. It's not anymore negative. So after this, it's pretty much like this, because the second degree inside eliminated the minus sign, which is, now I'm dealing with a 4, just like the one before, but I'm using green here to show you that something happened here. It's not negative 4. And the story continues. Apply the square root, you get the square root of 4, which is 2. So negative 2 as an input gave me, after applying two things, squaring and square root, the same output too. As you could see, you start at negative 2, you end up with 2. And that means that the square root of x to the second is always positive. And that shows what's happening, and that's absolute value. So that's one of the rules that we have in math, and we keep it always clear. Whenever you take the square root of x to the second, it's not x. It's one of the mistakes that sometimes students make. You have to be careful, because you don't know if this x was negative. If it's negative, x to the second will make it positive, and you could go on as it happened right here. So what kind of function family is this? It's an absolute value, right? It's a V shape, right? How do you write it as an equation? Y equals absolute value of x. Okay, let's take it when n equals 3. Same concept, same style, but n equals 3, which is odd. Again, we're going to focus on a negative 2. X, apply the cubic power. You get x cubed, take the cubic root, apply the power of 3, then take the cubic root, you end up with the cubic root of x to the third. And it's like a two-step process. Plug in 2, start with 2, cube it, that's 8. Take the cubic root of 8, that's 2. So you start with 2, you end up with 2. And that's right here. You start at 2, your final output is 2. In a different way, what I'm writing here is the cubic root of 2 to the third is 2. Which means you start at 2, end of the process, you end up with 2. Let's go for negative 2 on the left side. Negative 2 cube it, you get negative 2 to the third, which is negative 2 times negative 2 times negative 2, and odd number of negatives multiplied together will keep the negative sign. That's a negative 8. As you can see, I'm using different colors because it's something that you have to pay attention to. Take the cubic root of negative 8. Yes, we can. And that's the answer, negative 2. So you start at negative 2, you end up with negative 2, right there. We started at negative 2, up here, and the output did not take me back to 2, up. It took me down to negative 2. So in short, the cubic root of negative 2 cubed is negative 2. Start at negative 2, you end up with negative 2. What does this say? What type of function is this? So whatever you start with, you end up with the same thing, right? That is y equals x, which is linear. To summarize what we are doing with the tables and the graphs, here is the summary. The nth root of x to the nth can be written as an absolute value if n is even. Stays the same as y equals x if n is odd. Let's take two examples quick. The 7th root of x to the 7th is x, where the 8th root of x to the 8th is absolute value of x. That's what you want to take with you. Let's move on. Here's something interesting. If we want to rewrite square root of x as a power, as an exponent form, well, we could assume that the square root of x equals x to the power a. Now we need to find a. To write it as an exponent form, I need to write it this way, but what would a be? Here's the steps, and the summary will be on the right side. Here we go. Raise both to the power 2 to cancel the second root right here, or the square root. Well, this and this will cancel. I'll end up with x on the right side, and the left side, I mean. On the right side, you multiply the exponents. 2 times a. I'm not going to write a2. It doesn't sound right, even though it's correct. So I'm going to write 2a. Well, this is x to the power 1, right? It's not shown, but we agree on it. If x to the power 1 equals x to the power 2a, the exponents should be equal because the bases are equal. So 1 equals 2a divided by 2. I get a equals half. Let's go back to the problem. So the square root of x equals x to the power a, but a equals half, so that's how you write it down. Of course, provided that x is greater than or equal to 0, because we can't have a negative here. Restricted domain. Let's go with the exponent form of the cubic root. Same style, same idea. We're going to assume that it's going to have the log of x to the power a, and we're going to try to find a. Same idea, so I'm going to cube this time, both sides, raise it to the power 3 to cancel the cubic root on the left. Multiply 3 times a, that's 3a. But same idea, x to the power 1 equals x to the power 3a. Same base. We're going to have to end up with the exponents being equal, divide by 3, and a equals 1/3. A summary of this says the cubic root of x is x to the power 1/3. Notice that here we don't have restrictions on the domain of x, because we could have negatives here. Alright, here's some examples. Rewrite the following expression that is given in radical form, that's right here, as an expression with rational exponent. Let's take a look. So if we write this as x to the power a, we could raise or apply the cubic power, the third power, to both sides to try to solve. This will cancel this, and we'll multiply 3 times a. I have x to the second equals x to the power 3a. Powers are equal, bases are the same, exponents, they have to end up the same. 2 equals 3a, divide by 3, so that a should be 2/3. So we started with this and we solved for a, and that's the answer. Let me support that in another way. So we have the cubic root of x to the second. If I take the 2 out, because we can switch m and n as exponents, the 2 goes outside. This is a cubic root, which is what we agreed on, right? X to the power 1/3. Now multiply m and n, you get x to the power 2/3, exactly like this. Now here's an activity, and as you can see, I write everything before recording. It takes a lot of time to write and clean things, but this way I could expose you to more examples and give you more info. Here's the activity. Complete the cells right here. In each row, in the last column, write x is greater than or equal to 0, restricted domain, or all real numbers for the domain, to describe the restrictions that result in equal terms for each row. Alright, now this is the 4th root of x to the second. This is the power 2 of 4th root of x. As an exponent form, what do you think? 2 over 4, right? X to the power 2 over 4 simplifies to x to the power half. Because we're dealing with x to the second, where n is even, we don't want to mess up with the minus signs and end up with negative answers. So we have to restrict the domain and write x greater than or equal to 0. Now this one right here, think about this and compare it to these guys and try backwards. Well, this one here, 3 over 4, that's a fourth root. 4 in the denominator means a fourth root. Regular 3 means power of 3. That's a power of 3, or differently this way. Because it's a fourth root where n is even. Earlier I was paying attention to the x, but also the fourth root. You want to make the domain restricted to x greater than or equal to 0. Now, same style, let's go faster. 2 over 5, that means fifth root of x to the second, or differently, fifth root everything to the second. Because 5 is odd, we shouldn't worry, so it's going to be all real numbers. This one here, the fifth root of x, that means to the power 1, because it's x to the power 1, or differently x to the power 1/5, just like this. All real numbers, because we could have negatives inside. Next, when you have the square root, for example, of a product, you could split the square root to both sides. This is a formal way, it doesn't have to be square root. It says the following: the root of a product is equal to the product of the roots of each factor. Let me show you an example. Square root of 25 times 4, you could split the square root, this is a product, it has to be a product, equals to square root of 25 times square root of 4. Now let's see why this should work. On the left hand side, square root of 25 times 4, if I could multiply 25 times 4, which is 100, square root of 100 is 10. Now I picked numbers that are perfect squares to show you that this should work. Square root of 25 on the right hand side is 5, and square root of 4 is 2. 5 times 2 is 10, same answer. Now a common mistake that students might make is when they see square root of 25 plus 4, they split them. No, it has to be a product. When there is an addition right here, you cannot do that. You can't say like plus here, and if there's a plus here. You could try it with numbers, as you could see, and test it. It's not gonna work. Okay, my last example. Extract the roots and rewrite this using radicals and using powers. Let's use radicals. This is a cubic root of 8 times x to the power 6. We're gonna keep the radicals. Here we're gonna get rid of the radicals. So how do we do it? Let's break it down as we said earlier in the previous slide. We could break it down. Those are the two factors as a product. But looking at 8 as 2 to the third and looking at x to the 6 as x to the second times x to the second times x to the second, you could see where I'm trying to take you to. So that is x to the second to the third, which is somehow it's going to end up canceling, right? Same thing right here. So if you take it out and cancel the power 3 with the cubic root, I end up with 2 here. This cancels that, and this cancels that, and I end up with x to the second here. So 2x to the second. Using powers, we're gonna try same problem, rewrite the cubic root as to the power 1/3 that we agreed on. Here we go. Now we could look inside as a product, 8 times x to the 6 as 2 to the third times x to the 6, and then apply the power 1/3 to both products inside. 1/3 times 3 and 1/3 times 6, which is 3 over 3. I know it's kind of small to look at, but I don't want to skip steps, that's why. And 6 over 3. 3 over 3 is 1, 6 over 3 is 2, and now I have the same answer. That should do it for this video. I know it's kind of lengthy, but I'm trying to cover enough examples and information for you. Thank you, and I'll see you in the next one.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.